Well, good evening. We're going to talk a little bit about SSL today. What is SSL? Well, it's Secure Sockets Layer. Let's talk a little bit about what is it, how do we define it, how does it work? Well, SSL came to be because there was a lot of risk that people were taking when you were sending traffic unencrypted over a network. I mean, you're going to have people that were developed the man-in-the-middle attacks where they could see what was going on, and while you could protect everything inside your firewall, you were not, until it got to the other end, you never knew what was getting there, and it affected data confidentiality, data integrity. So the problem was we didn't really have any privacy. And there was tons of different operating systems in play at the time. You had Windows 2000, Windows NT, Windows 98, Windows ME, Windows XP. And there was just a ton of different operating systems, basically from SSL1 to SSL2, which was the revision of SSL1. SSL2 came out only 5 months, 6 months after SSL1. That just tells you how many problems there really were. So when they developed it, they developed a 3-layer solution. You have platform independent, application independent, and then session layer security. So that's what comes into secure socket layer. So let's talk a little bit about the client architecture, and so you can kind of understand where we're coming about. Now, SSL only really resolves on IP and TCP protocols because it's connection oriented, connection based. Unlike UDP, where that's connectionless, you have to have that connection so that you can send the challenge and the responses, or the request and the responses of those sessions. Okay. You can also have a proxy based, where you have an active relay where I can call up Steve, who is my IT person, who can call the other end. Okay. That Steve is acting as my proxy in this instance. It's an active relay. The proxy can change and modify the parts of the protocol and redirect those requests. Then you have tunneling, where you put it in the L2TP, or the point-to-point tunneling protocol, where you have that passive relay where it's encompassed in the encryption. So how do we do this? Well, there are 3 different layers that we have to look at. We have to look at the network layer, the transport layer, and the application layer. Application layer by itself does not have an SSL or really much of any security. The only security there is PGP, and pretty good privacy. We'll talk about that here in the next segment, about PGP and why it's not really all that it's cracked up to be. That's what your local encryption of your Word document would be. I mean, it's very easy to break, very easy to get into, and it's not the best for security. Then transport layer, your layer 4 protocol, can give you your tunneling protocols, IP sec. You can do PPTP or L2TP over IPsec, and that's your IP-based security. But then that leaves HTTP and SMTP and TCP virtually unsecured. Then we had our networks layer security, where we have our HTTP becomes secured with this secure sockets layer, and all the TCP traffic and IP traffic that translates over HTTP is secured in that way. So what does SSL do? Well, it negotiates and employs an essential functions for secure transaction. In other words, it gives you encryption, it validates the integrity, and you have that mutual authentication between the two ends, whether you're the client or the server, your server, whatever it may be, that you have that mutual authentication. You agree upon how the mechanisms work. Then you have the principal economy of the mechanism. You want to make sure that the security mechanisms are as simple as possible. You don't want to go to the level of an AES 256 type of encryption. You want to make it very simple, step by step, and make it so it doesn't overload the system. Then you have the principle of psychological acceptability. Security mechanisms should not make the resource more difficult to access than if the security mechanisms were not present. In other words, you want to make sure that John Doe can work on the system that has no security, and he can work on the system that has the security, and he sees no difference. I mean, that's what security should be. That's psychological acceptability. And you'll need to know the difference between the economy of mechanism and the psychological acceptability. SSL, though, like we said, added 3 parts of the security. It added the mutual authentication. That's where it establishes that trust relationship. The acknowledgement and receipts come back and say, okay, who they are, say they are. Okay, the server will authenticate to the client authenticates the server. It's a mutual authentication. Both say who they are and they validate it. Okay, we have data encryption, which means that the data is encrypted as it is transported across this length or network segment. And the integrity means that no one's tampered with it, pretty much. No one has touched it, no one has changed it, no one has modified it. Remember, integrity is part of your CIA triad. So let's talk about the difference between SSL2 that came out in 1994 and then SSL3 as it came in. Well, SSL2 had weakened authentication keys, 40 bits. It had a vulnerable message authentication algorithm known as MAC. And it had the block cipher attack, which left the padding link field unauthenticated. So I could guess where things were at, and then the cipher suite rollback attack will allow you to go in there and figure out the SSL encryption. So what was SSL 3? Why did we go to SSL 3? Well, we went to it for several different things. First off, we went for cryptographic security. SSL should be used to establish a secure connection between the two parties. Given, right? We have to have that secure channel between the two if we're going to be sending information back and forth. Interoperability means there's a programmer who's creating an application should not have to worry about someone else's code. That protocol should work no matter which way. The extensibility. It needs to have a framework in which the new public key and bulk encryption methods can be incorporated if necessary and when they are necessary. So we don't have to create a new protocol for all these different types of authentication. Relative efficiency, which means you want to make sure that it's very sleek, very narrow focus so that you're not going to have to kill your system, like we talked about with the psychological John Doe, that you want to make sure that you're not giving any extra emphasis to it to where it's going to make it more intensive, because as cryptographic operations do, because by default it's a mathematical scheme and the system has to go through all these millions and millions of types of information to break it down. So you want to make sure that it's completely efficient in what it's doing. So you don't want to give it this long algebraic formula that won't work. So here's kind of a way for it to happen. Public key cryptography for authentication. A random message that you're sending from A to B. Well, unless you know exactly what you're encrypting, it's never a good idea to encrypt something with your private key. It's pretty simple. If you don't know what you're going to do with it, then don't do it. Encrypt. The solution, we used message digests, or MD hashes. A digest is difficult to reverse, and it would take them a long time to even do it if they even have the same digest value. So what do? Well, with the MD hashing, we came up with what we call a one-way hash function. It's basically a digital fingerprint and a checksum. It's impossible to derive the original text from that hash, so you can't take the system's hash, reconfigure it, and find out what the information was. Okay? The basic requirement for a cryptographic hash is that the input can be of any length, the output has a fixed length, no matter what the original. If I had when we hash your passwords in the NT LAN manager, they hash your passwords. It's always going to come out a certain length. No matter if you have a 36 character password or an 8 character password, it's still going to come out to be the exact same length. So you're never going to be able to undo it. The hashing algorithm is relatively easy to compute for any given X amount, which means the input length. It's a one-way. That means it's only going to go one way, and it's collision free. Well, there are two different types of hashing types. We have asymmetric and symmetric. Asymmetric is very slow, very independent, because your encryption and decryption processes are two separate things. And encryption and decryption is typically 1,000 times slower than a symmetric one. And the reason being is because you have to exchange the symmetric keys back and forth, back and forth to get everything undone. Where symmetric, everything's done simultaneously. So it's going to be a lot faster. You can do a lot more bulk information with it. And that's what the difference is. What are the layers of SSL? Well, we have a record protocol, namely the connection-oriented protocol, TCP, IP. You have to have that reliable connected protocol. It's going to be encapsulation of everything higher than what it is at, so whether you're talking layer 3 or layer 4, and it's going to include the fragmentation, compression, and MAC encryption. Then we have the alert protocol, which conveys the severity of the message and the decryption of the alert. Gives you if you have anything wrong with it. Handshake protocol, which you hear all the time, that's that authentication between the client and the server. Who's going to, what are the security attributes? How are we going to send this information across? And then we have the change cipher spec protocol, which always carries a value of 1. And it's agreed upon during the session state. So what is a record protocol? Well, a record protocol encapsulates everything from the higher level. It is connection oriented, so it provides that TCP or IP based connection. And you have that one session at least with each computer, or the client or the server. You can have multiple connections, you can have one connection. You have to have at least one for it to be a record protocol. Okay? So here's what we have. We have the fragmentation of everything above it, and it gets compressed into a MAC. The MAC gets sent in with the data. The MAC is added to the end of it. All that is then encrypted. Then you have the record header, and then that's sent out. So that's how the process flows of your data. Session parameters. Well, session parameter has session identifier, which is the sequence chosen by the server. It's like a SID, just gives you an idea of what the process is. A compression method, how are we going to compress it? To what level? The cipher spec, are we going to do DE, triple DES, DES, AES? What are we going to do? The master secret is the secret shared between the client and the server. That's your decryption algorithm. And then is resumable. Is this state going to be resumed or not? You know, does the user have to redo it if there's a connection lost? SSL resumption. That will distinguish between your one-to-one or TCP connections. They're all virtual. The handshake is expensive, therefore it's allowed for multi-threaded browsers. And you really don't want to do much SSL resumption. You'd rather it quit and then they have to reinitialize. SSL client authentication, you'll have to do a re-handshake. And then there's what it means by expensive is there's a lot more stuff that has to go on behind the scenes, so your process keeps going over and over and over. Here's an example of a TCP dump. This is clean text, secure, unsecured text that would happen. The client synchronized with University of Tulsa. The server came back, said University of Tulsa said, okay, we're good. The acknowledgement of the synchronization back from the server. The client requested something. The server acknowledged it and sent the first packet down to them. So there's your first 6 packets. Now, let's take that same TCP dump, but let's put it in an SSL. Here's what's going to happen. You're going to have that TCP connection. It's going to send the hello to them. And then you're going to get the information that says, okay, which way are we going to do it? We're going to do it RC4, we're going to do RC2, triple DES, DES, MD5. What kind of algorithms are we going to work with? Packet 5 is just an overhead. Packet 6, then the server sends back how they're going to do it. They're going to do it with SSL RSA4, 128-bit MD5 encryption. with the and they're not going to have any sort of compression in this authentication. It also sends the handshake certificate and the server hello done certificate. Packet 7 is just some blank overheads. Packet 8 is the return from the client saying, here's my key, for it to do what it needs to do. Again, 9 is the little overhead. 10, the server gets that information with the cipher spec and the handshake and does it again in 11. And then by 12, it starts sending from the client down to the server, or from the server back down to the client at packet 13. So you can see there's a lot more that it has to do with. So here's the handshake algorithm, or handshake protocol. The client says hi to the server. The server says hi, sends all the information, its certificate, key exchange, certificate request, and its hello is done. It just says, here's all I can do for you. The client comes back and says, here's what I need. And then I'm finished telling you what I need. The server says, okay, here's how we're going to do it, and I'm done. So that's how they agree upon everything. So phase 1, it initiates the establish the security protocols. You're going to look at the version. It's going to find out what the highest SSL version understood by the client is. Whether if the client only gets to 2.0, then it's only going to go up to 2.0 from the server side. You're going to have a random 32-bit timestamp and 28 bytes are going to be secured by a random number generator. And then you're going to have a session ID. Again, the server will give you that session ID number. Then you have the cipher suite. It lists all the combination of crypto algorithms supported by that client in decreasing order of preference. So the first thing it wants to do the RSA or Diffie-Hellman. Then it wants to do triple DES or AES. Then it would go down to the MAC algorithms, which is your SHA-1 or your MD5. So here's the different ways that it wants you to do. And then it finally says, okay, what are my compression methods? Here's what I'm going to do. Then the server sends its hello back to them and saying, I understood, here's everything I got. Phase 2. The server performs the authentication and key exchange. It can send an X509 certificate. It's optional, but it's not necessary if it's an anonymous Diffie-Hellman, if that's what they're going to use. And the server key exchange message, not necessary to fix for the Diffie-Hellman or the RSA. And then a certificate request message specifying the signature schema as well as a list of accepted security authorities. And then it sends its hello done and says, hey, I'm done. The client gets the information, says, okay, here's my certificate message, here's my key, and here's how I want to verify it. The server gets it, says, okay, I'm going to change your cipher spec message. Here's what we're going to agree upon. Here's what we've done. Now I'm sending you my change cipher and my finished message. The finished messages are basically just hashes of the secret keys in the whole handshake protocol, excluding the messages, of course. But basically it just says, here's how we're going to do it. Now they've agreed upon it, and they've got that connection established. So what kind of applications are we talking about here? We're talking about HTTPS, which is HTTP over SSL. SSL or S-Tunnel, which is an encryption wrapper for network daemons. SSL Wrap, which is the same thing as SSL Tunnel. It's more of an encryption wrapper. S-Telnet is the secure telnet. Do you want to use SSH over Stelnet? I would. I would not, because it's lower encryption. So try to use Stelnet if you can. SFTP, which is going to be your secure FTP. Samba servers use SMB for Unix platforms. Bind, if you're going to use DNS security via OpenSSL, and that was what was getting hit a little bit with Heartbleed. Then you have SendMail, which is going to be your SendMail MTA, or your message transport authority. And then you have your SSL VPN, which is going to be your IPsec type stuff. So here's another view of how it works. The client says the server to hello. The server says hello. It says the key exchange, and it says that it's done. It's given everything it needs to do. The it concluded as part of the negotiation. The client will then send the session key or information back to the server in what we call a client key exchange. The client sends the cipher change cipher spec message to activate those negotiated options. Then it says it's finished. Let the server check for newly activated options. The server then sends the cipher spec message back to the client, as well as it's finished, saying everything is ready and set and go. So, what are some SSL implementations that you might see? Well, JSSE, which is from Sun, it's just a Java extension of SSL. You have Pure TLS, which is by Eric Rescorla. You have Icyclic, which is from IAK. And then you have SSLJ, which is from the RSA. SS Lava, which is from FAOS. NJSS, which was Netscape. And then you have OpenSSL. And as y'all all know, OpenSSL had a lot of problems with Heartbleed, and it's since been patched. But what is SSL's problems? Well, you can end up spoofing SSL. SSL depends on certificates, which can be spoofed, because usually you can go from a trusted certificate authority, but I can create my own certificate. So is that a good thing or a bad thing? And to allow certificate authentic or CAs to scale the ability to create an SSL certificate is delegated to intermediate CAs, which means the high-level CA isn't going to do it. So you have a lower-level CA that's doing this, and so that's really some vulnerabilities. Now, IE did not check those extensions properly. Therefore, in IE5 to IE6, it was fixed in 7, so you haven't had this problem since, but it's still it becomes a pretty serious problem. And then we have thoughtcrime.org. I'm not sure if that website still is in existence, but they have a program called SSL Sniff. It's a man-in-the-middle attack, and you might want to go see if it's still out there. If it is, download it and see what you can do with it. Might be interesting. And then we have Transport Layer Security, or TLS, and SSL. They're both data encryption protocols. TLS is SSL's 3.1. TLS is the new SSL. It's developed in an open community standard. It is backwards compatible with SSL, but SSL is not compatible with TLS. So keep that in mind. TLS allows secure and unsecure connections over the exact same port. Is that good or bad? Think about it. And it works great for POP, IMAP, as no port changes are needed. Well, I hope you enjoyed this brief view of SSL, and if you have any questions, email me.